Hi guys, as I promised in my previous video, I am going to show you how you can create a simple neural network using Python. And you know the great part about this? We are not going to use any external library other than Python's inbuilt libraries. How cool is that? So let's get started. Open your project folder, create a new folder called neural network, open it, open your IDLE, create a new file, and let's first save it. And I'm going to save it inside the neural network folder. This one, and I'm going to name it neural net. I found this picture in the internet which is pretty much explaining the neural network in brief. Let's save it, and yeah, so you can see in this neural network we have three layers. One is the input layer, this one, and in between the hidden layers and the output layers. So the first thing we need to create a layer of neuron is a neuron. So we have to create a neuron first. So let's create a neuron, class neuron. You can see this neuron is getting inputs from previous layer of the neurons. So to initialize this neuron, we need this information of this previous neuron. So let's create the constructor with self, and we need the previous layer. I'm calling it layer. And you know, these inputs are called dendrons and this output is called the axon in the biological term. So I'm calling this input connections as dendrons. So I'm creating dendrons self dot dendrons as a list so that it can hold multiple neurons, and this neuron has to know how much error it produced while giving the output. Self dot error, for the error I am setting it to 0, and it has to produce an output. So for that, sub dot output, and again setting it to 0. Now for the back propagation we need something called gradient descent, which is like in which direction the weights has to shift so that it can minimize the error. That is called gradient descent. I will tell more about this later. So, gradient, I'm setting it to 0. Now you can see this input neuron has no previous layer, so we can set a condition here. If layer is none, it doesn't have to construct the connections. If the neuron is the input layer, it doesn't have to create any connection. But if the neuron is not an input layer, it has to create the connection to the previous layers. So if the layer is none, we will pass, else we will create the connection for neurons in layers in layer. Now this neuron has to create a connection to this neuron. This connection will include this connection information will include which neuron it is connected to and what is the weight of the neuron connection. And one more thing for the momentum calculation, it is the change in the weight that is occurred in the previous calculation. So before creating any connection, we need to create a connection class. So let's create a connection class first. Connection. And what we will need here is only the neuron which is connected to, which is the connection is pointing towards, self and connected neuron. So self dot connected neuron equals connected neuron. And we need the weight of the connection equals, I'm setting it to random, or you can set it to any value for initial stage. Self delta weight or you can say d weight to make it short, and for the beginning it's 0 and done. Now we can continue our construction of network or connections. So let's create a connection first for the first neuron. For the first okay, make a neuron for the first neuron in the previous layer. So connect con equals connection, and we have to give the neuron here. So it will create one connection, and we will append this connection to its dendron list. Let's append it. Dendron, sorry. And now we are done. We have created all the connections that are available in the previous layer. When we feed forward, the neuron has to collect all the inputs from its previous layer. It has to sum those inputs and pass it through some activation function and creates an output. So let's create the feed forward method then. Def feed forward self sorry, it has to be here. So what we have to do, we have to collect all the outputs of the previous layer. So let's loop through the previous layer. First we need to create a sum variable, sum of outputs equals 0, and now for each neuron in the dendrons, we will get its output. Sum equals neuron dot output. We have to accumulate it, so sum plus neuron dot output. Okay, sorry, this is not the neuron, this is the connection, right? So it has to be for each dendron in the dendrons. It is calling each one of its dendron, and from that dendron we are calling this connected neuron. So dendron dot connected neuron, it is calling its dendron, and that dendron is calling its connected neuron, and from that neuron we are getting the output. Now after getting the output, we have to multiply the weights of the dendron, that how much the dendron is amplifying that output of the previous neuron. That is the connection weight. We can get that multiplied by dendron dot weight. Okay, so this will do this sum operation. It will collect the output, it will multiply with the weight, and it will sum all these values. So now that we have some of the outputs, we can generate the output of our own. For that we need a transfer function. The transfer function we are going to use is a sigmoid function, which is generally used in neural network. So a sigmoid function looks something like this: 1 by 1 plus, okay, let me show you. Sigmoid. So this is the sigmoid function. What it does, it limits the output value between 1 and 0, but its speciality is it is a continuous function. So we are going to use this sigmoid function. We need 1 by 1 plus exp minus, sorry, I don't know what I was doing. Sorry. I have to give the function name. Let's call it sigmoid, and this is x, and it will return 1 by 1 plus, we have to use this e to the power x. In Python we have a method for that. We need to import the math library math. So now we can use math.exp of -x, and we have our sigmoid function. Now that, one more thing, it has to be self. Okay, now that we have our sigmoid function, we can use it in our feed forward method. So the output self dot equals sigmoid of sum of outputs. Let's make it a decimal value, and done. So we have updated our output and we have created the output. So we are pretty much done with the feed forward. Now we have to do the backpropagation algorithm. In the backpropagation, what the network is doing is, okay, let me open the Wikipedia page. Backpropagation. Let's open it and let's go to the main equation here. So what is backpropagation? It actually does is we will supply the error or target value to the output neuron. It will then check how much error it produced with respect to the target value, and according to the error it will adjust this W1 and W2 so that the error next time the error will be minimized. But it will tell its previous neuron that, boss, I'm not the only responsible person here. You guys are also responsible. You guys gave me wrong inputs. That's why I generated some error. It will send the proportion of the error that each and every neuron in the previous layer contributed to it. So that is called backpropagation. Updating the weights and sending back to the previous neuron that its contribution to the error. So how we can do that? Let's see. So this is called the gradient, and the gradient is error multiplied by the derivative of the transfer function we have used. We have used the sigmoid function. If we get the derivative of the sigmoid function, this is the sigmoid function, and if we search the derivative, it is sigmoid function itself multiplied by 1 minus the sigmoid function. So here you can see the output and 1 minus the output. So it is the derivative of the sigmoid function. Well, enough talking. Let's start with the backpropagation method, and I will explain it while writing it. So let's backpropagate. So we have to calculate the gradient, which is self dot gradient equals, for the output neurons the error is output minus target. For the hidden layers we have to calculate the error in a different way. We will see that later. For now the error is in the variable in self dot error multiplied with the derivative of the transfer function. To make it more proper, we can just define the derivative of sigmoid. Let's say it d sigmoid, and self x, it will return x multiplied with 1 minus x. So if we supply sigmoid x, it will just derivative the sigmoid function. So now we can give a sigmoid, d sigmoid, and self dot output. You can see it is same as this function, where we have, instead of this function, instead of calculating the error this way, we have already a variable called error. We will store that error value there and we will use that here, and instead of directly writing the derivative, we are calling it inside a function. So we are good with the gradient. Now we have to update the weights. Let's get back to this picture. we have calculated the gradient. Now we have to update the weight. So for that, we have to run a loop for all the dendrons that this neuron is having currently. That is for dendron in dendrons, and sorry for the mistake, this has to be self.dendron. What it is going to do, you can see that for the change in weight, it calculated the partial derivative of the error with respect to the weights, which is here the gradient multiplied by the output. So the output, which is I, means the output of the previous neuron and the gradient of the current neuron. So that will make the partial derivative of the error. So we need to get the output of this neuron, and we need to get the gradient of this neuron. So gradient of this neuron we have already calculated it. So we need to get the output of the previous neuron that we are currently updating. So the change in weight, dendron dot d weight, which is delta weight, sorry, is it here, delta weight equals dendron dot connected neuron dot output multiplied by, you can see, output of the previous neuron, which is I. Let's say this is I and this is J. So output of the previous neuron, OI, and the gradient of this next current neuron, which is DJ, del J, or whatever it is. So let's multiply it, self dot gradient. So this will create the delta weight. And in this Wikipedia page, something is missing, is called the momentum. So we have to add the momentum to it. That is, okay, first you can see that this is the partial derivative of error we have calculated, but we also need a constant. This constant is called the learning rate. This is called the learning rate, alpha, but we are going to call it eta here. That is widely used, and this constants are common for all the neurons, so we will make it a class variable. So eta equals, let's make it 1.9, which is very high actually, and I'm going to add another variable, alpha 1.5. okay, let's give some comment here. Let's okay, this is momentum rate, and let's move it. Okay, so we have calculated the delta weight. Just we have to multiply the eta here, which is neuron dot eta, because it's a class variable, and this is not written in the Wikipedia page, but most of the document books you will see this, that we also need a momentum variable, a momentum rate for the delta weight, that is alpha or neuron dot alpha multiplied by the previous delta weight, which is dendron dot d. What this part will do, this part will keep pushing that change in momentum in the direction it is already going. So we have calculated delta weight. Now we just have to add the delta weight to the weight. Dot weight equals dot d weight. We have to add that delta weight, not assign. So previous weight plus the delta weight is the new weight. We are done. We are done with updating these weights, but we have to tell this previous neuron that I am not the only one to blame, you are also responsible for the error. So for me you have generated this much of error. So this neuron have to give this neuron its contribution to the error, which is, and one more thing, this neuron, in this case there is only one neuron. So let's say this neuron needs to know how much error it produced. So it has to get its contribution from this neuron and this neuron also. So we need some method which will accumulate the errors to this neuron. Let me show you. Let's create a method called add error. And what this will do, this will just accumulate the error to its error variable. Plus error. So now we can use this dendron dot weight equals dendron dot connected neuron dot add error. Now we have to send this neuron its portion of the error, which is the gradient of this neuron multiplied by the weight of this neuron. Means if the gradient is positive, that means we need more output, and if the gradient is negative, that means it should decrease its output. Self dot gradient, and so that means this neuron is telling this neuron, you have sent me more values, you have contributed more to my error, and if this weight is less, so it will say your error contribution to the error is less, so you will have to suffer less. This will be a multiple, and with this we are done with the back propagation. But before ending this method, we need, this neuron has adjusted its weight, so Now it will set its error that boss, I have done my part, I have adjusted all the weights. Now I think I am clear, I have no error. So I have to make my error 0. I will declare my error as 0. So with this we are done creating the neuron class.